Bonjour. So today I'm going to talk about the blockchain or blockchains. Not sure if that's a word or a concept. We are going to talk about cryptocurrencies, Bitcoin, and a big warning up front. I'm not going to talk about speculation. I'm not going to argue about which coin is better than the other ones. I'm not going to tell you which ICO you need to invest in. I'm mostly interested in the technology behind the blockchain, trying to understand what kind of problems it solves and if it is useful for something. Because apparently, if you have a look at the new projects out there, most of them have a blockchain somewhere. So it looks like we have found a magic wand that is able to solve all the problems of the world. That's great news, right? And I'm a bit skeptical. So, to really understand what we are talking about, what a blockchain is, what kind of problems it solves really, let's dive into the details of the Bitcoin protocol and the core technologies. So today we're going to talk about not just the concepts, but about the technology behind the scenes, and we are going to try to build a blockchain with PHP, and we are going to try to build a coin, the Fab coin, of course. That makes sense, I think. It's very valuable, and I have a lot of them. And if you want some, perhaps at the end of the talk, you can come to me and I can sell you some for a lot of money. Okay, so the main concepts of the blockchain are, I think, quite easy to understand. It really comes down to a few things, and when you put them together, all of a sudden you have something that is really powerful. But you really need to understand that it was created for one use case. And it's very good to solve this use case, which is the Bitcoin or any alternative coin. So just to be clear, using a blockchain is almost never the solution for your problems. Okay. Okay, so let's start now. So we're going to talk about digital money. That's the main usage of blockchains, of course. And one of the very first experiments was DigiCash. It was in 1989, I think. And it went bankrupt 10 years after that, so in 1988, which is 20 years ago. So it was a first experiment, and it went bankrupt because it was probably too early, so nobody was actually using this digital money. But it was nonetheless a very interesting experiment, and we learned a lot because as soon as the company went down, the money, bam, disappeared. We had nothing. So even if you add some coins, some money, digital money in DigiCash, all of a sudden you had nothing. So what we learn is that having something that is centralized does not work for a digital money. So we need something else. And of course, the something else is Bitcoin, which is another experiment, I would say. And it solves some of the problems that we had with DigiCash, and mainly centralization. So Bitcoin is really about three different concepts. The first one is identity. The second one is decentralization. And the third one is network consensus. And we are going to talk about the three different concepts today. I remember, I think it was 5 or 6 years ago, I was here downstairs somewhere doing a talk about HTTP, and back then I recommended to read the HTTP specification. I don't know how many of you have actually read the specification, the HTTP specification. Okay, I think I need to give up. The good news is that this year I'm going to recommend you to read the Bitcoin white paper. It's only 8 pages long. It's very easy to read, very easy to understand, and hopefully after the talk it's going to be even easier to read. You will see the main concepts and which kind of problems Satoshi tried to fix. Okay, so talking about digital money, let's create one really quickly. I'm gonna switch to my okay, let's have a look at the code. So I have a code here, that's plain PHP. This JSON file is where I'm going to store all the balances of everybody. So I don't have the file right now. If the file does not exist, then I'm going to give me a lot of coins. And if it does exist, then I'm just loading the balances. Then we have 3 different methods. The first one is to get the balance of someone. The second one is to create a user. So yeah, that's plain PHP. That looks kind of weird. If there is already a balance for the user, then that's for 500 or whatever. Go away. If not, we give the user 0 coins, and then we have a method to transfer the money from someone to someone else. And of course, we're trying to avoid someone getting under 0. Make sense? I think we're done. So let's try if that works. I need to go to a browser. Okay. Okay. So we are not going to try that now. For a couple of reasons, and the first one is that I don't have the web server running, so it's not going to work anyway. Okay, so that's an implementation of the digital money, very simple one. There are a bunch of problems, right? Can you spot some of them really quick? Yeah. Authentication. Yeah, of course. Authentication. But we could add some username passwords or something like that. But of course, we would need some kind of, you know, credentials. Yeah, something else. Yeah. Something else? Yeah, on my machine, yeah. You trust me, right? I can steal the money very easily. If I close my laptop, money is gone. Yeah, bye-bye. So, that's a lot of problems, a lot of challenges. So the first one is, I think the very first problem is that there is no blockchains, right? That's a big problem. No blockchains, it means, you know, the value is 0. It's local only, so availability and reliability is not there. Again, if I close my laptop, it's gone. It's a single point of failure. Authentication, of course. We could add passwords. And trust. If it was on a server, a government could ask me to shut down the server. It could, you know, shut down the server as well. So we need something that does not depend on a third party, really. So the very first problem I want to talk about is availability, and I'm going to talk about that through decentralization. And that's probably the most important one, and one that made DigiCash a failure, really. So removing that means that I want something that is not depending on a central server. I want something that depends on a network of servers or machines, really. And I want to be able to add more servers or more machines or remove machines, and the network should still work. So one way to do that is, so we want to go from a client server that is very familiar in the HTTP world, where the state is on a centralized server, and then you have clients talking to the main server, to a state where we have many servers talking together with a shared state. And that's the main point here. We want the state to be on every server, so that if a server leaves the network, that's not a problem, right? Because the state is shared on all the servers. And to do that, we're going to use what we call a GrUSP protocol. A GrUSP protocol is very easy. I'm talking to Stefan. He's reading his tweets. So I'm saying something to you, and then you're talking to someone else, and at some point, everybody is aware of what I'm talking about. But it can take time, right? It can take time from the information to go from here to over there, right? So that's the main issue with the GrUSP protocol, and one that we are going to talk about a lot today. Okay. The great thing about the GrUSP protocol is that even if I am the first machine in the network, if I start to add more machines, I can leave the network. That's not a problem, because everybody has all the information about the state of, or all the information that we want to share between all the servers. Okay, so let's forget about money for a minute, and let's take another example. Let's say that we want to share the best talk during PHP Day, right? So I know that my best talk is mine, whatever. Stefan liked to talk about the messenger component, yeah, okay. But the thing is, over time, we are going to change our mind, right? The conference is not over, which means that you can change your mind, right? And we want information to be shared between all the participants. So let's create a GrUSP protocol with PHP. That's the second example I have here. I'm going to close that. Okay, so I have the state. So state is a very simple class here. It takes a user. A user is really just that, when we are going to print something on the screen, it's easier to understand. We have a port. That's the port I'm listening to. So we are listening to a port, and then we can have a peer. That's a peer I need to connect to the first time. So the very first one doesn't have a peer, of course. That's the first machine. But then when you want to connect to the network, you have a port, and you need to know at least one peer port. Then we have a bunch of sessions stored in a file. Nothing fancy here. And then if there is a port, and if I don't have a state yet, then I'm updating my state. And basically, if we have a look at the update main method, we get a random session, and we increment the version. Why do we need a version here? The thing is, it takes time to propagate the information. So if Stefan says, I like the session about the workflow component, and then 10 minutes later he said, no, I like the messenger component session more. As it takes time, I might think his best session is still workflow, but the new one is messenger, but I'm not aware. And someone else has already the new information. So when I get information from two different people, one is going to say, okay, Stefan likes the messenger component session more, and someone else is going to say me something else. How can I decide which information is actually the latest one? That's why I need a version. I'm going to keep the latest version of the information, right? Okay, so the thing is, the network is going to be eventually consistent. And that's the key point here. Okay, and then I'm going to store my state, and that's all. Okay, now I have a loop. I'm looping forever, and I'm going to communicate with each peer I know of. So at first it's going to be one peer. If it's me, I'm not going to talk to We're going to continue, and then we're going to encode the state, and we're going to post our state to the peer that we know. Okay? And the state here is really about my port and my peer port. So I'm going to send all the information. And of course, my best session, of course. Okay, so here, let's have a look at what we are doing here. So we are creating a state for the user, and then we are going to update our state based on their state. Okay, and then we are going to send back the state of the peer, right? So if I'm communicating with Stefan, I'm going to send him my state. He's going to update his state, and then he's going to send me back his updated state, right? Everything is okay? Okay. So how do we update the state? And that's the important thing here. So we iterate over all the information that we get from the peer. If it's me, I'm not going to update anything, of course. We are checking that the data are actually correct. And then, if we know nothing about the peer, then we just set the state. And also, if the version is more than the current version that we know of, right? That's the two possibilities. Okay, if we try to do that, so here, on the left, user Fabien, that's me. I'm going to run gossip.sh. Basically, the script is doing something really easy. It tries to find a port, an available port starting with 8000, and then running my gossip script forever. Okay, let's try that. So I'm here, and as you can see, I'm changing my mind over time about which session is the best, and you can see the version number before the session name. Okay, I'm trying to connect now another port, so it's going to be Ellen, and the peer is Fabien. And if everything works, they are going to start to talk to each other, and at some point you can see that they know about the session, the best session about the other one, right? I can add another one, and this one, Thomas, he knows about Ellen peer, he knows nothing about Fabien, right? But as he's going to start to talk to Ellen, Ellen is going to say, okay, I know that Fabien exists, and then is going to communicate as well with Fabien, right? And of course, I can then kill Ellen, for instance. I mean, the process, of course. And as you can see, it still works. No problem, right? I can run Ellen again and kill the first node. Still works, right? That's the gossip protocol. Okay? Okay, let's go back to the slides now. So, what we have achieved now is fault tolerance. We can add more machines, we can remove machines, it's not a problem. The thing is, there is a problem, or there are many problems. The first one is that someone can tell me that Stefan's best session is something with a very high number for the version. If someone does that, I don't know that the guy is not Stefan, and Stefan is not going to be able to override anything because the version number is really high, right? So there is a problem. So we need some kind of authentication, but using a username and a password does not work anymore. Why? Because we are sharing the state, which means that I don't want to send you the password, my password, and you don't want to send me your password. So that's a big problem. We can't use usernames and passwords anymore. So what we need to do is to find something else, and what we're going to use now is cryptographic identities. Basically, what we need is a public-private key. So the public key is the equivalent of the username, and the private key is the equivalent of the password. There is a big difference between public and private keys and username and password, and the big difference is that there is relationships between the public key and the private key. Okay? If I give you the public key, and the public key is public, so you can share it, that's not a problem. And of course, you don't want to share the private key. That's the password, really. If I sign a message, if I encrypt a message with my private key, I can send you the message, and you can decrypt the message with the public key. But here, I'm not that interested in encrypted messages, because the fact that I'm sending you some message is not something that I want to hide from the network. It's public as well. What I want to be sure is that you sent the message. So what I want to be able to do is check that the person who sent the message is actually the right one. So if I can check with the public key, and the way to check that is to decrypt the message and check that the message is the same as the non-encrypted one. If the two are the same, then I know that you actually signed the message with your private key, which means that nobody can actually forge that, right? If you want to forge something, then it means that you have the private key of the guy. If not, then the public key will not be able to decrypt the message and check that it is actually valid. Okay. Do I have? Yes, I have a demo of that. So let's have a look at the code. So here, it's quite simple, because with OpenSSL support in PHP, there is nothing fancy to do. So the first thing I wanted to be able to do is to create or generate a pair of public and private keys. That's how you can do that. I'm returning the private key and the public key. I need a way to encrypt a message, to decrypt a message, but more importantly here, I want to check that a message is valid. And to check that a message is valid, I need the original message, unencrypted, the encrypted one, and the public key, right? And if when decrypting the encrypted message with the public key, I get the same value as the message, then we are sure that the message was actually signed by the private key. So here, the encrypted message is more like a signature, really, and not really used for encryption. So now, using the thing, we generate a key pair, the public key and the private key. We have hello world as a message. We encrypt the message. We print the encrypted message. We decrypt that, and then we check that the message is valid. Okay, let's run that. So that's the public key. And by the way, that's exactly what you get when you create a Bitcoin account, wallet, whatever. You have a public key, that's your public identity, and then you have a private key, the encrypted message, which is really a signature, the decrypted message, and it is valid. True. Okay? Okay, let's go back here. So now, we have a peer-to-peer network with the GrUSP protocol. We know how to have an identity on the network with cryptography. But there is a problem. There is a problem because I can lie very easily. I can say something here, I can say something else there, and you will be able to check that I'm the one who actually said that because I've signed the messages, but I've sent two different information. And remember, if you are really far away in the network, it's going to take time to actually propagate and to find that there is a problem. For the sessions, that's not a problem. For money, that's a big problem. Let's say I want to give you one coin, and I'm going to give the same coin to someone else at the same time. You will be able to check that I am the one who actually sent the thing, the coin, but you won't realize the problem until you are trying to spend the coin again, and then the network is going to say, no, the coin is not yours, it's there. Okay? So, and that's the double spend problem, and that's the main problem solved by the Bitcoin protocol. Right? how can I be sure that a coin is not spent twice? That's the main thing. So how do we solve that? The first way to solve that is with a central bank. If you have a central bank, then it's very easy. I'm going to send a message to the bank, but if I'm going to send the message twice, the bank is going to say, no. You already spent a coin, no way you're going to spend it again. Right? But we don't want that. We want something that is decentralized. Okay, so how can we fix that? There is one way, is that when I'm signing the message, I'm adding a word from the newspapers of today, so that I can be sure that when you decrypt the message, you can check the newspaper and be sure that it was actually signed today. It's not very practical, of course, but that's one way you can solve the problem. That's not a way we are going to use today, of course. So, to do that, we need some kind of coordination between all the nodes. And as it takes time to propagate the information, if we are able to slow things down, if we are able to wait for the information to propagate everywhere in the network, you would have realized that the coin was spent twice, right? So at first, what I want to do is to be able to slow things down. Remember that, and remember what people are saying about the Bitcoin protocol, the thing that you can spend money really fast. That's a lie. That doesn't work. I mean, right now. Okay, to do that, and that's something really great. We are going to use what we call proof of work. That's how it's called in the Bitcoin world. And so the way we are going to coordinate is that we need to make the transaction slower. So to do that, we need a way to slow the computer that is actually sending the message or creating the transaction, really. That's what we call mining, but before getting there, let's have a look at how we can slow things down. Okay, one can say that using PHP is a great way to slow things down. That's not enough. So basically, we want a CPU to do some work, so we need to find something that is really slow. A CPU is really good at solving math problems, so that's what we're going to do. I don't want you to read the screen now. So the problem we want to solve is something that is really easy to create, but very hard to something that you can't. Okay, so you have a value, you want to do something, and the result is stable. So if you have the same input, you always have the same output. We want something that you can't guess, so if you make a slight change in the input, the output is totally different. But we also don't want you to be able to go from the output back to the input, right? And that's something we can do with hash functions, right? So if we can do something like hash SHA-266 and hello. Okay, so same input gives you the same output. If I slightly change the input, the output is going to be totally different, and there is no way you can go back from the output to the input, or at least we think so. It depends on the hash function you are using, of course. But as you can see, even in PHP, that's really fast, really fast. So it doesn't solve the problem. So instead of doing that, what I want is I want to find a nonce, which is really a random string, random value. And when I'm adding the nonce to the string, I want the hash to contain a number of zeros at the beginning of the hash, right? So let's try that. Let's A, no, that's a C. Let's B, no, that's the 8. 1, no. 2, no. Yes, right? I have 1, 0. So I need to try a lot of things to have 1, 0. Now I want 2 zeros. I'm not going to try that by hand. Instead, we're going to code something. So here, to find a nonce, what we're going to do is we are going to check that the nonce is valid, and checking that is computing the hash of the message with the nonce. And if it starts with a certain number of zeros, then that's okay. Let's try with 3 zeros. And the nonce is really just an integer that we are incrementing over time, right? And then we have the message, hello world, and we want to find the nonce for the message. We are printing the nonce, which is really the number of iterations that we need to find something that works, and then the hash. Okay. Okay, so we need 500 iterations to find a hash with 3 zeros at the beginning of the hash. If we ask for 4 zeros, oops, it's going to take more time and more iterations, and if I ask for 5, takes more time. You get the point. That's exponential, actually, right? That's how I can slow things down, and it means that depending on the number of zeros, it's going to take more time or less time. So we can adjust the complexity depending on the number of zeros that we want at the beginning of the hash. So it's not going to work. Okay, let's go back here. So that's mining. That's not really the solution because, oops. Okay. It's not a solution because I can still double spend really easily. I'm slowed down, which means that it takes more time for me to create 2 transactions, but that's it. Just take me more time. So that's not really the solution. We need something more than that. And the more than that is a blockchain, at last. So the blockchain is really just a number of blocks chained together. So in a block, we have the message, we have a hash, and we have the previous hash. So the list is actually linked, which means that to add a block to the blockchain, you need the previous hash, and you need to find a hash starting with x zeros, and the message that we want to hash is actually composed of the message plus the previous hash. Okay? Okay. And the great thing about that is that if we shuffle the blocks, the blockchain is not valid anymore, right? Because the previous hash is not going to be the right one. So now we have solved the problem because we have an order, right? So if I create the first transaction, which is block 2, if I want to create another transaction with the same coin, it's going to be block 3 after block 2, right? So we have ordering now. Yeah? Okay. And that's it. That's a blockchain. A blockchain is just a linked list with hashes. It does not solve any problems other than the double spend problem. That's it. It's not a database. It's not a distributed database. It's not, right? And remember, all the nodes in the network, they have all the information. The state is shared by all nodes in the network, right? Okay. We still have some problems, of course, and the problem is that I can fork the blockchain. So remember, I have block 2, I can create block 3, but I can create block 4 with the same previous hash as block 2. So I can have a fork at some point. So how can I decide that block 3 or block 4 is actually the right chain, right? And that's where everything clicks together. So, and that's the beauty of the Bitcoin protocol, really. You will see that solving that problem is so easy. The rule is very simple. The rule is that you always keep the longer chain. The chain where there are the most blocks. Why? Because remember, to create a block, you need to spend some CPU time to compute a hash, right? Which means that creating a block takes time. Now, if you want to fork and you want to double spend a coin, we are a large number of people participating in the network, of course. So you have the first transaction, and people are going to do other transactions. So blocks are going to be added over time. If you want to fork the chain at some point, you need to keep up with the chain to be sure that you have the longest chain so that it is accepted. If you are not able to keep up, it's going to be discarded at some point because the longest chain is going to win at some point. Which means that if you want to fork the chain, what you need to be able to do is to have more CPUs than the rest of the network. So basically, you need to have more than 50% of the computational power of the network, which is impossible, right? And that was the vision of Satoshi in his white paper. Everybody should be able to participate in network, which means that forking the blockchain is almost impossible. Is that the case now? No, it's not. It's not because now we have mining pools. So all the people, so you don't have the blockchain on your laptop anymore. That doesn't work. You can't mine bitcoins on your laptop anymore. That's not possible anymore. Which means that we have a few big companies that have a lot of power in the network. That's why when you are doing a transaction with Bitcoin, you need to wait, or that's a recommendation really, you need to wait at least for 6 blocks to be created after the block where your transaction is in to be sure that the transaction is final. If not, there is always a possibility for a fork somewhere. And forks happen naturally because in the Bitcoin world, we send transaction to all the nodes, and all the nodes are actually competing to create a block, which means that at some point you can find the same solution at the same time, which means that the same transaction or some transactions are going to be in the same blocks linked to the same previous block. But remember, the longest chain wins, which means that at some point one of the block is going to be discarded, right? Okay, I think we have everything we need to create a cryptocurrency in PHP. Are you excited about that? Not really? Oh, first, let's have a look at a very simple blockchain. So here, the proof of work is really the same class as before. Here we have a block. The block is a message. A message is something. Here, just a string. The previous block does not exist for the Genesis block. The Genesis block is the very first block created in blockchain. For the previous block, we just want to keep the hash, that's all. Then we have the message, and we mine the block. Mining means finding a nonce that allows to have n number of zeros for the hash. And more important is the isValid method, where we are checking that the nonce is actually valid, right? So we are checking that the message plus the previous hash with the nonce actually give you a hash with the number of zeros that we are expecting, right? The blockchain now is even simpler than that. That's just an array of blocks, and you can add a block here, you give a message, it creates blocks, that's all. And checking that the block is valid is very easy. We are checking that for each block, the block is actually valid, right? And then we also check that the previous block hash is the same as the hash of the previous block, right? Okay. So, creating a blockchain, you create the first Genesis block, then we add 2 blocks, we are checking that the blockchain is valid, and then we are trying to shuffle the blocks and check that the block is not valid anymore. So if we run that, Okay, so you can see here the first block, there is no previous hash. You have the nonce, which is the number of iterations to get 4 zeros at the beginning of the hash, and the message. Then you have the second block. You can see that the previous hash is the same as the hash of the previous block. And then we have hash, and the blockchain is valid. And if we shuffle the blocks, then the blockchain is not valid anymore. Right? Okay. Fabcoin. So the block is almost the same as before. The big difference is that now we want to store transactions. Okay, so a transaction is very simple. We have a from, so that's the public key of the sender of the money. It's nullable because for the very first transaction there is no from. We are creating money out of thin air, right? Then 2 is the public key of the receiver of the money, the amount of coins I want to send, and the private key of the sender, so that we can actually sign the transaction. What we are keeping in the state is the from, the to, the amount. We can't, of course, store a private key because we can't share the private key. So instead, we are creating a signature, which is the encryption of the message with the private key. And the message is the from, the to, and the amount. Okay? That way, we can check if a transaction is valid without the private key, checking that just that the message, which is the original message, encrypted, the signature, which is the encrypted version of the message, and we are able to decrypt this signature with the public key of the sender. If that's the case, then the transaction is valid, and you can't forge the transaction, right? So transaction is not forgeable. We have the block to store the transaction. We have the proof of work to be able to create a block. The blockchain is almost the same as before. We can add now not a message but a transaction. The isValid method is exactly the same as before, except that now we are also adding something to be sure that you can't add a transaction where you are sending more money than what you have in your wallet. That makes sense, right? Okay. So I'm not going to talk about this method. It's really easy. We are just iterating over all the blocks and checking the balances. Okay, we still have the GrUSP protocol, same as before, so we can talk to each other. And the state that we are going to share is composed of all the peers that you are aware of, plus the full blockchain. Okay? Proof of work is the same, PK is the same, key is just a small abstraction for the public and private keys, and that's all. So here, remember, we have the loop, and we are talking with all the peers we are aware of. We are not going to talk to us, of course, and then we are giving our state and updating our state with the peer state. So the important part here is how do we update our state, and especially blockchain. So here, if we have already a blockchain, so that's not the first time we are actually communicating with someone, then we are updating our blockchain with their blockchain. If not, we are just getting their blockchain as the initial value. So how can we update the blockchain? Very easy. If the peer has no blockchain, we are doing nothing. That's the fork rule. If their blockchain is smaller than our blockchain, we just ignore the blockchain. We don't want to have to update anything with their blockchain. If their blockchain is not valid, it means that there is something going on. We don't want to update our blockchain. If that's not the case, we are just overriding our blockchain with their blockchain, right? So as you can see, the code is really simple, easy, nothing fancy really. And then As before, we have a small file to create a user, trying to find a port, and then starting the loop here. I also have a small file here to be able to send money from someone to someone else. Okay, let's try that. So I'm gonna create a user Fabien here. So you can see the network at the top. There is nobody now. I have 1 million Fab coins right now. And you can see the blockchain. So that's the Genesis block. None means that there is no previous block. No, it's not the previous block. None is, that's the from, that's the public key of the from. There is no from because I'm creating money right now. So FSTK, etc., that's a small part of my public key. And then I have 1 million Fab coins. You can see the nonce and the hash of the transaction, right? Of the block, sorry, the block. Now let's create another user, and it's going to be connected to Fabien. As before, the GrUSP protocol is going to do its work, so they are starting to communicate with each other, and you can see that the blockchain is the same for all the users. Let's start another one, and they will all communicate together. Now, I'm going to transfer some money from me to Ellen. I'm doing that on my node, so that's the first node. And you can see that at some point, that's eventually consistent. So we have the same information everywhere with the same blockchain, and everybody is aware of all the transactions, really. If I'm trying to send a lot of money I don't have, then it's rejected by the network, right? Just because the blockchain is not valid. So when someone receives a blockchain that is not valid, it's discarded, right? I could try to fake something by creating a fork node, and that's much more involving, so I don't have time to do that. But you can try to do that, trying to fork the network and having two different blockchains, and you will see that at some point the longest chain is going to win, right? Just because more work actually happen in the longest chain. Okay, so we are running out of time here. What you are seeing here is almost what happened in the Bitcoin protocol and in the nodes. Of course, it's a simplified version of that. The main difference, or there are many differences, of course, but one of them is that when you mine a block in Bitcoin, you have more than one transaction in a block, right? So we get a lot of different transactions, and we are trying to get them into one block. There's also a big difference, and the big difference is that creating a block means spending CPU time, so you need some kind of incentive to do that. So we have not talked about that, but the node that actually is able to create a new block in the blockchain get some coins back just for the work. So we have not talked about light clients, because of course if you are trying to use that kind of thing on your mobile phone, you can't have all the blockchain on your phone. That would not make sense. It's huge, it's big, so there is a way to actually get only part of the blockchain and still be able to check that the blockchain is valid. We have not talked about Ethereum and the fact that you can have code directly embed into the blockchain. That's another world, I would say. That's kind of like having a virtual machine directly into the blockchain. So whenever there is a transaction, some code can run and do things, and you also have some data that you can store directly into the code. So there is more to explore, but hopefully just with what we've talked about today, you have a better understanding on how it goes out behind the scenes, and you will probably have a good read with the Bitcoin white paper, because everything I've just talked about is exactly what is contained in the white paper, really. Okay, last time I'm going to switch to the slides. Okay, and that's a quote from me, actually. Yeah, that's almost never the technical answer to your current problem. How many of you have bitcoins? Okay. How many of you have bitcoins just because they are using bitcoins as a means of sending money or receiving money? 2, 3 perhaps, that's all. And that's the biggest problem right now. The network is really slow, so if you want to make a transaction, it takes a lot of time to get the transaction actually mined and part of a block. And if you would need to wait for 6 blocks after that, it takes a lot of time, really. And doing a transaction from a bank to another bank, especially here in Europe, it's much faster. And it costs nothing. At least in France, doing a wire transfer costs nothing. That's not the case with the Bitcoin protocol. If you are sending some money to someone, there is some fees associated with that, and the fees are going up just because there are so many transactions that when someone mines a block, he wants to include the transaction with the better fees, really, so they can get more money. So you also have fees. That's a problem. And so there are many things that are ongoing here to try to fix those problems. And the Lightning Network thing is probably one of the most interesting one. So if you want to learn more about Lightning Network, I really recommend you to you go to Google, and there are plenty of information about that, and that's pretty interesting. But it's getting more complex over time, so I'm not sure it's going to end well. Anyway, thank you very much for listening, and if you have any questions, I think we still have a few minutes to do that. Thank you.